Good evening, everyone. I'm very happy and honored to be here with you this evening, and I would like to thank the NUSTEM team for this opportunity. So today, as announced, I will talk about complex and intelligent systems. So the aim of this lecture is ambitious and simple at the same time. So I would like to show you, by an example, how mathematical abstraction, inspired by natural phenomena, by the observation of a natural phenomena, simple natural phenomena like boiling water, magnetization, allows to build machines whose behavior correspond to the exercise of the faculty we call thinking. So the question is how to build machines which independently can make decisions, and make decisions which at least make them look intelligent to some extent. So this is the plan of this talk. We will look at the first side of the story, the natural phenomena which are of interest for us this evening. So phase transitions and complexity. I'll tell you about examples of phase transitions in fluids. In particular, I'll tell you about the van der Waals equation. So phase transition in metals, I'll tell you about spin models. And then I'll try to show you how spin models can be viewed as intelligent systems and can be further developed to create models of associative memory. And this an example of a model of associative memory is called the Hopfield machine. We will run together an experiment to show you how the Hopfield machine works, and then we'll go through some conclusions and research questions. So, okay, what about phase transitions? Actually, all of us experience phase transition on a daily basis, I would say. So we're all familiar with the fact that matter presents itself in different phases. For example, water can be a liquid, can be a solid, ice, or it can be a gas like steam, vapor, and a metal could be either just an unusual metal or behave like a magnet, so attract other metals. For example, the magnets on your fridge, if you have any of them. And we're also familiar with phase transitions. For example, you look at boiling water, and you know that when the water reaches 100 degrees Celsius and a temperature of about 100 degrees Celsius, it starts creating these bubbles, and then it evaporates very, very quickly. Okay, so something happens when you reach this specific temperature. Something happens in the water globally. Okay, so if you think about water as made of water molecules interacting between each other, so at the microscopic level, water molecules always do something very non-trivial. So they move around, they interact, they move around. But at the macroscopic level, so if you look at a glass of water or a saucepan of water, like this one in the picture, so nothing really happens. But then there is at the critical temperature, something starts happening. So the molecules interact in such a way that globally, if you look at the water as a whole, starts changing, turning into something else. Okay, so you go from an ordered phase where the water appears as a liquid and fills a portion of the container, to a disordered phase where it evaporates and the gas goes everywhere. Okay, so this is an example of a phase transition and an example of how complexity emerges under specific conditions. So complexity has to do with a system made of a large number of particles, and these particles under specific conditions, like this famous 100 degrees Celsius, start behaving collectively and do something together. Okay, and a priori there is no clear reason why this should happen. So this phenomenon, although it is a very familiar phenomenon, probably since the discovery of fire. So the first theoretical description and understanding on how this phase transition, say gas-liquid phase transition, occur is very recent, and it goes back to just the early 20th century, early 1900, and it is due to Johann Diederik van der Waals, so a Dutch physicist, who, as part of the work of his PhD thesis, he discovered this equation here, with which we are probably familiar, at least in a particular case. So this equation is very important because it relates in a very specific way. So three main thermodynamic variables which define the state of a fluid. Think about water, for example. So this is the pressure P is the pressure in the fluid, V is the volume, T is the temperature. R is a constant. It's called the universal constant of gases, and N is a chemical. Is the number of moles, a chemical unit of mass. A and B are constants. So are specific parameters that depend on the type of the fluid. So A basically accounts for the interactions between the molecules, and B is related to the volume occupied by each molecule. So if you assume that the molecules are very distant from each other, as it happens for a so-called rarefied gas, you can set A equal to 0, and then if you neglect the volume occupied by all the molecules, just the molecules, the size of the molecules, you can set B equal to 0, and this will give you the equation, the famous equation for the perfect gas, PV time equal to nRT. So this means that if you keep the pressure constant and you increase the temperature, the fluid will expand. If you keep the temperature constant and you increase the pressure, the volume will reduce. Okay, so the gas, the fluid, the liquid will be compressed. If you look at what this equation looks like on a graph, a way to do it is, for example, to plot the pressure as the volume changes when you fix the temperature. Suppose you do this for a high temperature, higher than a critical value. And so, for example, above 100 degrees Celsius. And then suppose that you look at your gas in your container of a volume V. And then you start reducing the volume of your container, so reduce the volume, and you look at the way the pressure changes. So the equation tells you that if you reduce the volume, the pressure increases, and the rate of increase actually also increases. Okay, so the pressure increases faster and faster as long as we reduce the volume. But this rate of change of the pressure changes if you reduce the temperature. In particular, if you reach a specific critical temperature, you see that a sort of plateau arises in this graph, in this plot. So if you reduce the temperature further and you repeat the experiment, you start from a volume here and you start reducing the volume, you see that at some point something very strange happens. There is a particular value of the volume such that beyond that value, you keep compressing your fluid, and then the pressure inside stays constant. So you compress the fluid, you're providing energy to the system, and it's not clear from this graph what's happening to this energy. So, and this is when the phase transition occurs. So the gas is compressed, the molecules are so close to each other that the so-called van der Waals forces play a role. So the molecules bind together, and then the gas transforms into a liquid. And then it takes all this way to complete the process. And then when the volume reaches this value, what you see is that all the fluid all the gas turned into a liquid, and then you see that the pressure increases very fast. And so this means that and this is something that we all experience. It's very easy to compress a gas, but it takes lots of strength to compress a fluid. So the van der Waals equation reproduces apparently only part of this phenomenon, because if you plot the solution to the van der Waals equation, what you see is that you follow this continuous line, and then you go into this dashed curve. Okay, so the pressure increases and then decreases and then increases again. Okay, so this dashed line here is not normally observed in experimental situations, apart from if you do the experiment under very specific and delicate conditions. So there is therefore a discrepancy between the theory provided by van der Waals and what you observe. This discrepancy was solved, at least partially, by an eminent scientist, James Clerk Maxwell, who suggested that the position of this plateau is such that the straight line cuts the van der Waals solution in two lobes of equal area. And this is known as the equal area, the Maxwell's equal areas rule. And he came out with this based on energy conservation of energy considerations. So if we look at the solution, then now I just want to suggest a little tweak. So instead of looking at the solution to the van der Waals equation as pressure, as giving you the pressure as a function of the volume, let's just flip this plot in such a way that you look at the volume as a function of the pressure. And then you see that above a certain temperature, the curve, if you take a value of the pressure, you have only one value or associated value of the volume. What happens below the critical temperature is that there are for a specific value of the pressure, you have more than one possible volume which satisfies equally the van der Waals equation. This means this curve like this tells you that theoretically there is more than one macroscopic state. A macroscopic state is a specific value of the volume associated to the same value of pressure. And this is very interesting because somehow, so the nature chooses at some point when you reduce the pressure, the nature chooses either one value of the volume, this one, for example, or this value of the volume at the top of this line. So this line in the theory, in the mathematical theory behind this equation, is called a shock. Okay, a shock is a sharp transition from one state to another. Now let's look at a different type of phase transition, which is from the point of view of the physics underpinning the phenomenon. The physics is completely different. So imagine you have a metal. Okay, a metal can be modeled as a lattice. So you can think of a squared lattice, for example, like this. And then at each side of this lattice, you have one atom of your favorite metal, say iron. Okay, and then the key point here is that each of these atoms carries a sort of magnetic charge. Okay, so each of these atoms behaves like a tiny magnet. Okay, so where the North Pole can point, where you have a North Pole and a South Pole, and then the North Pole can point in the upward direction on the downward direction. So if you represent this in picture, you basically we look at this lattice, we look at each atom on the lattice, and then superimpose this magnetic charge, which is called the spin. Okay, and therefore this is a spin model where we organize magnetic charges on this lattice. Okay, so if you look at a metal and you look at you zoom to look into the microscopic state of what is happening in this metal at the microscopic level, what you will see will be spins. Okay, pointing randomly in all directions. To simplify things, we assume that spins can point either upward, so the North Pole point upward, or downward. Okay, So the red is pointing upward and the green is pointing down. And to some extent, the spins behave exactly, move around randomly, so up and down, similar to what water molecules would do in a gas, and they can arrange themselves in different ways. For example, under suitable conditions, so these spins might decide to work together, okay, so interact and work together to point all of them in one direction. In this case, you will have a phase transition from a situation where all spins point in all directions in a disordered manner. So if you have many of them, roughly 50% of them will point down, 50% of them will point up, and then if you add all these magnetic charges together, you will get overall a zero macroscopic magnetic charge. If the spins, for whatever reason, decide to point all in the same direction, and you add all this magnetic charge together, you will get a non-zero magnetic charge. And then the overall, macroscopically, your piece of metal will display a magnetic behavior, okay? Will behave like a magnet, like one of the magnets on your fridge. There are different ways to model this. You can think of the spins interacting pairwise according to the same with the same strength. Okay, this is called Curie-Weiss model. Or you can simplify things in a different way by assuming that each spin interacts only with the nearest neighbors. Okay, and does not feel the strength, the interaction with the others. In this case, you'll talk about Ising model. So in the following, I will consider a case where a simplified case where all the spins interact with the same strength. All pairs of spin interact together with the same strength. So how do we study magnetic models? So a convenient way to do it is to look at the macroscopic state, okay, in order to decide which phase the system is, this metal is at a particular time. A way to do it is introduce the notion of order parameter, which gives you an idea about the state of order or disorder of the spins on the lattice. A natural order parameter is calculated by taking the sum of all the spins divided by the total number of sides. So in this way, if 50% of the spins point upward, and then 50% of the spins point downward. So the total, if you add them all together, you will get the same amount of minus ones added to the same amount of roughly the same amount of plus ones, and then you will get zero. So the order parameter will be zero, telling you that the system is completely disordered. Okay, so there is a random distribution of spins pointing up and down. But if the spins decide to point in the same direction and you add them all together, say all the spins point up, the sum will be equal to the number of sides. If you divide by the total number of sides, you will get 1. So the order parameter will be equal to 1. So the expected value of the order parameter is denoted by m, and then it's a function of two things. So the coupling constant, so the strength of interaction between pairs of spins, and the temperature, and satisfies, at least in an approximation, to this cubic equation. So you know that a cubic equation admits at most 3 real solutions, and this depends on the value of the coefficients. In particular, in this particular case, it will depend on the value of this constant, J divided by T. Suppose for a moment that the strength of coupling is equal to 1, okay, just to fix a number. And then we want to look at how the solution to this equation, this cubic equation, changes if you change the temperature. So in particular, you will find that if the temperature is higher than a particular value, in this case it would be 1, so you have only one solution. So this straight line here corresponds to the 0 solution. So m equal to 0, if you substitute here, is indeed a solution. And there are no other solutions. But then if you reduce further the temperature, you reach a point here where Beyond this point, the number of solution increases. So the solution m equal to 0 will still exist. Okay, so you actually see, and this is represented by this orange curve. So m equals to 0 is always a solution regardless the value of j and t. But also two extra solutions appear. So one given by this branch and one given by this branch. So basically, if you fix the value of temperature somewhere in this region, so you will see that there are, similarly to what we observed in the van der Waals case, in the case of a fluid, you have three possible solutions, three possible macroscopic states. So a disordered macroscopic state, m equal to 0, and then two more ordered macroscopic states corresponding to a positive value of the order parameter and a negative value of the order parameter. This order parameter is also called magnetization. Okay, so how do we understand this? Why does this happen? So a general principle actually helps us to understand that. And a general principle of nature is that any physical system tends to relax, okay, to reach the equilibrium, an equilibrium where the point where the energy is minimal. If you look at a thermodynamic system is a system of interacting particles, of many interacting particles. There is another quantity which describes the general behavior of the system, and it's called entropy. And the entropy is this quantity called S here. The entropy is basically a physical quantity which measures, in a way, the degree of disorder in the system. So the higher is the entropy, the higher is the degree of disorder of a system. So, for example, if you put like a 1 liter gas in a 10 liters container, the gas will expand and will fill the whole volume available, increasing the amount of disorder. So nature tells us that it feels more comfortable in a state where the energy, in particular the internal energy, which is basically the energy associated to the interaction between the spins, is minimal, and the entropy is maximal. So a convenient quantity, the free energy, it is a convenient quantity which allows us to identify the state of equilibrium by minimizing this difference, U minus Ts. If you minimize the free energy, the internal energy minus temperature times the entropy, this guarantees that the system reaches a state where the internal energy is minimal and the entropy is maximal, because if the entropy is maximal, minus Ts will be also minimal. And then if you plot the free energy as a function of the order parameter, you will see different behaviors. So if you look at the system at high temperature, for example, this red curve, you will see that the free energy has only one minimum in the case of the spin model, in the case of this magnetic model. So there is one minimum, and this minimum corresponds to the order parameter equal to 0. So this minimum is associated to the equilibrium of the system, corresponding to a completely disordered situation where about half of the spins point down and half of the spins point up. If you decrease the temperature, so this curve, the red curve here, becomes the orange curve. You still have one minimum only, but tends to be flatter and flatter. Beyond a particular temperature, corresponding to this orange curve, something interesting happens. So below this temperature, so the profile of the free energy changes dramatically, and you see that the minimum, what before was a point of minimum, so the magnetization equal to 0, becomes a local maximum. Okay, so the magnetization decreases if you move from the green dot to the left or to the right, and two new states, two new minima appears, closer to -1 and closer to +1. So In this situation, the green dot here corresponds to the zero solution here, and the additional dots here corresponds to this branch, okay, to these branches. So these are two additional states, and this tells you that this minima, the system, will most likely find itself in a situation where the free energy is minimal. So either on this left-hand side or on this right-hand side. And somehow, depending on the conditions, the system decides whether to collapse around this state here or around this state here. For example, if you shake the distribution of spins, so for example, you heat the metal, or you shine some light on the metal, so you will shake the configuration of spins, and then you will find your system in a configuration that is not in equilibrium, and then slowly or fast the system will tend to reach the equilibrium. So, for example, if you start from a situation where you shake the spins and you are in a situation corresponding to this yellow dot here, so this system will evolve, okay, will change in order to reach the lowest, the closest minimum, okay, in the direction where the free energy decreases. Okay, so the yellow dot will prefer to go down this valley rather than going uphill and then down to reach the other point. Okay, so somehow the spin, you shake the systems, and then the system makes a decision whether to accommodate itself on the right-hand side or the left-hand side. Now, a natural question arises is, can we use similar mathematical rules, so for describing the interactions between the spin, and get what is called a free energy landscape, a richer free energy landscape, where instead of having just two minima, you have more than one minimum. Okay, so as for example in this case. And then the problem we pose today is the problem of being able to build an intelligent machine, so like the spins do, so they make a decision whether to accommodate themselves in one state or the other, using similar mathematical rules as for magnets, in such a way that the landscape is richer, as in this case, and the stable configuration, so the minima, can be associated to a meaningful information, a distribution of spins which is associated to a particular piece of information. For example, the memory of an image. So therefore, there is what we are going to exploit is a natural map from a spin configuration, and the information associated to it. So the way you do it is to look at the spin configuration as a pattern. So, for example, you have this arrangement of a 5x5 array of spins, randomly oriented, and then you can associate to each spin an array of pixels, black and white pixels, where, for example, the spin up correspond to a white pixel, and the spin down correspond to a white pixel, and the spin down corresponds to a black pixel. So this configuration here corresponds to a pattern, okay, to an image. Okay, so and the spin model becomes a mechanism, an effective mechanism to store specific pattern. So because the minima will correspond to specific arrangements of spins, and therefore to a specific pattern. As this type of problem of devising a mechanism for associative memory was developed by John Hopfield, so a physicist and biologist who developed what is called nowadays the Hopfield's machine. And the foundation of this can be found in a paper from 1982, published in the Proceedings of the National Academy of Science of the USA. So what is the idea of the Hopfield machine? So imagine you have a pattern. Let's take a simple one. So this pattern of 4 pixels arranged in this way. +1, say that +1 is white, -1 is black, -1, +1. And then you map this pattern into a spin model, okay, where each site here, each node of this graph, if you want, contains one bit of information, +1 or -1. So +1 corresponds to the white pixel, -1 to the black pixel. But in addition, so these spins here interact in pairs. Okay, so these red lines correspond, telling us that these spins interact with each other. So how do we represent effectively a pattern? What we can do is to just place next to each other, so the rows of this array next to each other, and then we compose a vector. So an array X, and in this case will be 1, -1, -1, +1. And the number of entries, this bit of information, is the length of the pattern. In this example, the length of the pattern is 4. And then what we do, we assign specific values to represent the strength of interaction between different pairs of spins or sites in this graph. Okay, so we will call each constant of interaction will carry a subscript that tells you which sites are involved. T12 for the site 1 and 2, T23 for the site 2 and 3, and so on. Okay, so in this model, then we have the nodes of this graph, so the spins and +1 or -1, and then the set or a set of parameters corresponding to the strength of this interaction. In this way, you can transform into a spin model, okay, or if you want a graph or a network like this, any information. So it could be, number 1, your number 7, like an irrational number like pi, your favorite singers, or your favorite cartoon character. Okay. So what the Hopfield machine does? So the Hopfield machine implements the following algorithm. So you take a pattern, a general pattern. So depending on the size of your image, you will have you will have a bigger array, an array of a longer array for bigger images. And for example, suppose if you have a pattern X given by n entries, X1, X2, and Xn. And suppose now that you have more than one pattern, so 3, 4, 5 P patterns of length n. So how do I distinguish between them? So I take X and then I put in a superscript, I call it S, and S ranges from 1 to P. So X with superscript 1 will be the first pattern. So the image of the number 1. S equal to 2 will be a second pattern, the image of the number 7. S3 will be a third pattern, the image of the number pi, for example. And Hopfield suggested to construct the coupling constants, these numbers Tij, using these patterns in this specific way. So you take the pairs of entries x, y, xj for each pattern, and then you add them all together. Okay. At this point, it's not clear why you should do that, but the result is indeed amazing. So then you start running now the algorithm. Step 1, you take an input, call it y, okay, a random input pattern. So you have the stored pattern x1, x2, x3, and so on, and they are stored through this rule by associating the patterns to the coupling constants. And then you take an input, and this input can be anything. So a random alteration of one of the stored patterns, or a road sign under poor visibility conditions, for example. And then for each entry, okay, of this input, we calculate this quantity. Okay, so you calculate the quantity delta I given by this combination of the coupling constants and the corresponding Ti1 and the corresponding entry y1. So y1 plus 1 divided by 2. And then you add them all, these terms, excluding the particular entry you are considering. Okay, so excluding the second index equal to I. And then you look at the value of this delta. So in the step 2, if this delta is larger or equal than 0, you set the entry equal to 1. And then if the delta is negative, you set this entry equal to -1. So basically, you have the input, you run the step 2, and and then you update this entry pattern, and then you iterate it until convergence. Let's run a computer experiment at this point to see exactly what we get. So first, I incorporate the pattern 1, okay, then the pattern 7, the pattern pi here, and then I take this initial pattern, and then I feed the Hopfield algorithm. As I feed this input in the Hopfield algorithm, I run it, and I get as a result the number 7. And this is actually interesting because in this line here, okay, this line here in the code tells you that the way I constructed this pattern is by a random alteration of the pattern number 2. So this pattern here, the number 7. So basically, I flip the pixel, I change from white to black or black to white, with probability 2/3, okay, 0.66, okay, and let's see how it works in reality, okay. Suppose, so this is the code I wrote. So let's take, just to speed up the calculation, an array, a 15 by 15 array, okay. So each side of the array is of length 15, and then I store, okay, I load the pattern, the first pattern, the number 1, okay. It doesn't look very nice because I took like a relatively small number of pixels. So this is the pattern 7, this is the pattern pi, okay. And now, okay, I just run the same under the same rule. So I flip the actually, let's suppose that I flip the pixels with probability 1 out of 20, okay? So you see, I start from 7 and I flip the pixels with probability 120. You see that the pattern, I can still see the original pattern I started with, 7. But then I do the same exercise with probability 1 out of 10. You see that the image becomes more disturbed, okay? So I can still see the 7, okay, but it is more difficult. Let's do the same with probability 1/5, okay? And then you see that the situation becomes more tricky. So, you know, I can't immediately, at least I cannot immediately associate this input to any of the stored pattern, okay? Suppose that I feed this into this input into the algorithm, okay, and let's run the algorithm. So I get 7 as an output. So then why it works, and also I will tell you why it doesn't when it doesn't work. So in the Hopfield algorithm works exactly as the spin model works. So the landscape of the free energy, okay, is more complex. I have more minima, and it is constructed in such a way that this minima corresponds to the pattern, okay, to the patterns I want to store. And then if I take a random alteration, my system will find itself somewhere, say here, okay, and then which is not a point of equilibrium. So then the system will tend to reach the equilibrium by approaching the closest minimum in the direction where the free energy decreases. So this yellow dot will accommodate itself around this minimum here. The thing is that the Hopfield algorithm, the Hopfield model constructed using this rule, allows automatically allocate patterns to minima, but also there are other patterns, okay, which are not associated, other minima, which are not associated to any specific pattern. For example, this combination of 1 and 7, this interference, if you want, between 1 and 7 we observed, can be one of these red dots. Okay, so there are spurious patterns which need to be taken into account. Okay, so but if the algorithm is properly tuned, okay, for a specific purpose, it can work very well. What we learned is that the Hopfield machine is an example of a neural network, so a sort of artificial brain, whose ability to make intelligent decisions depend on the complexity emerging for simple rules which govern the system at a large scale. Okay, so you have simple rules for the spin interactions, and the complexity, the ability to identify a specific pattern instead of another, is a complex emergent property of the system, which occurs when you take more and more a larger and larger number of spins or pixels, or if you want, neurons. A variety of neural networks and machine learning algorithms nowadays exist. They are available and deployed on a daily basis to help with the solution of a variety of specific problems, medical diagnostics, big data, trading, and so essentially any area of human activity has been exposed to the power of artificial intelligence. So a natural question is that, do these systems actually think? Probably not yet in the way we think of. But the key point is that at the moment we don't have a full understanding of this system. What do I mean by full understanding? So by full understanding, I mean that we don't know in the detail for systems of a certain complexity, the detail of the landscape of the free energy. Although we can use computer simulations to explore portions of the landscape of the free energy to fulfill a specific purpose or a specific task. And the current research expresses the need to go back to the foundation to develop a new fundamental mathematical approaches, a deeper understanding of complex systems.